Hello there guys, it's Jumpre here, and welcome back to another episode of Late Night Maths. So today we're going to be looking at vector spaces, and there are going to be various chapters on this, covering various things. And today we're going to do chapter 3 and then come back to chapters 1 and 2 later, and then chapter 0 are much later, and then chapter 4 might come out before 1 and 2, but I'm not sure. But essentially all that's covered in 1 and 2 is just the definition of a vector space. But you don't actually use that much for this topic on subspaces anyway. You just use that you have a vector space with a definition, and then you just find a subspace using a few facts, a quick theorem we have that allows us to find a subspace without having to go through as much work as it is to find a definition. So that was a lot of words, but don't worry about it. We're just going to start on subspaces. But unfortunately, before we can get into any of the interesting things with them, we have to go for a bit of terminology. So we have subspaces, vector space, and we have a set of 3 key terms that are going to get thrown around a lot, both in this chapter, next chapter, and maybe like chapter 5, I think, as well, maybe? Because there's going to be some more interesting proofs in chapter 4 for sure than here. We're not really going to be proving much in this episode chapter thing. We're just kind of look at what the definition of a subspace is and when to show something's a subspace. And then maybe episode 2 of this chapter we can do an example. Alright, so it's quite philosophical, these first 2 items. There's 7 items total, by the way, on this episode. These are the first 2. Hopefully I can get everything done in about 20 minutes, but we'll see how it goes. Got a timer going so I can see my progress. So I've decided I'm only going to get about 4 minutes to talk about this, because as much as I can talk about this for a while, this particular section, I want to make sure I'm as concise as I can be. So I don't know how much of you guys watching this will be maths people, computer science people, or neither, but we're going to be using the syntax from Java, which at the top of your class you'll say, and if you don't know what classes are, don't worry, but you can say some object extends another object extends another object, and the idea is the more you go this way, the more it's specialized. So a vector space is a special type of vector space, which is a special type of a set. So I mean, this probably isn't the most helpful example ever, but whenever I think about this, in computer science we call it an is-a relationship. In maths this just kind of gets left on the side implicitly, but I felt it was useful to make it explicit just for this section, because otherwise it can get very confusing on what's a vector subspace, vector space, or a set. Is you can say, one example is, yeah, I'm running out of desk space, so my keyboard is on top of my computer. So the Control Z button when I want to undo is up there. It's kind of weird. I'll get used to it. So one example is toast extends bread. And what this essentially means is we can say that toast is a bread, or toast is bread, but bread is not toast, because toast is a special type of bread. And this is the syntax I've got for that. So we got a vector subspace is a vector space. So if it's a vector subspace, you know it's a vector space, and you can sometimes use the property as a vector space is on a vector subspace. And in fact, that's actually the definition of vector subspace, but we'll come to that in a second. Furthermore, we have a vector subspace. Sorry, a vector space is a set. So a set is just a set of items, and a vector space is a special kind of set, which is going to be useful when working with them as an object. And then I've come up with this notation of crossing it out to say it's not something. So a set is not a vector space, and a vector space is not a vector subspace. Although I've got an asterisk here because technically a vector space is kind of a vector subspace, but the question is what's it a subspace of? The notation we're going to be using, we'll get this in just a second, so I'll write it here. When we do definition 3.3, so I'll say let U be a subset of V. Oh, and if you're like lost at all, when I go back and do chapter 0, which you should be able to find when you're watching this in the playlist, it'll go into like prerequisites, and that'll make this not comfortable. The main thing is vectors, a bit of linear algebra, and sets is what you need mostly. But I'll cover what you need more in detail in chapter 0. So we'll say let U be a subset of V. I like to use a lot of symbols. Then for U a subspace of V, which we use this notation, and then we continue. So we're using this whole idea of the is-a relationships because we're saying they're sets, one's a subset of the other. When is it a subspace? Well, we'll look at that in a second. So there's one more thing I need to do for item 3.1, and I've lost my notes. I give myself 1 more minute to cover items 1 and 2. I might not be able to, but hopefully. Alright, I'm saying I think there's maybe a few other is-a relationships I could write out, but these are the main ones. We're saying set is not a vector subspace. Just to be complete and just to give an example and make it interactive by writing something. Okay. Oh, and I'll cover this in chapter 0 again, my notations video, but essentially I use this to say end of a thing that isn't a proof, because I like drawing squares, so just a square with a line for if it's not a proof, but ending it. So we got item 3.1. Item 3.2, so I just quickly wants to talk about vector spaces in a sort of different perspective. There's sort of maybe 4 main ways you can look at a vector space. So you can just say let V be a vector space, and that's a vector space. In the same way you might say let, don't know, A0 equals 0, and then you might use A0 in a sum later on, so you might say B equals 1 plus A0 equals 1 plus 0 equals 1. If this looks too basic for like the level of maths, honestly, with abstract algebra, with like rings and modules and stuff, like sometimes you do come back to basic examples because it turns out the real numbers is a field, and that can be used for various things. This is a general field here. It could be the reals, it could be another field. So the 4 main ways we can look at a vector space is we've got either we can put it in words, we can say this thing, which we'll talk about in a second. We could just say V, and we've already said it's a vector space, so we're kind of referring to it. This is sort of a way you'll see a vector space coming into existence. And the other thing you can do is you can just do a set of both a field and V, and this kind of implies that the operations vector addition, I guess you can think about this, scalar multiplication, addition over the fields, and then multiplication over the fields. But it doesn't have to be multiplication and addition over the fields, it can be any 2 operations. You just have to give them symbols. So I like this notation. I've not really seen it anywhere, it might be somewhere, but it just kind of makes it very explicit what things are going into making a vector space. So I tend to use this because I like to be a bit more verbose than this notation, but I sometimes use this notation because it's nice and concise. You just write 2 things and you're done. Alright, we've made it through the the dense logical hell of that. If none of that went in, I can try re-recording this episode at a later date and try and get these explanations better, but hopefully the combination of the symbols and me talking has maybe made that just about stick. Okay, so now we continue with the main meat of today, which is no proofs today, unfortunately. We're doing proofs in later episodes for sure, and the prequel episodes as well, in chapter 0 and 1 and 2. But today we're just going to go over some how we have subspaces, how we show them, but like a top level overview. So we've done the first 2 items, and then to continue we are going to do definition, which we've already written a bit of. We're going to do a notation. Going to do a theorem. Going to do lemma and then a remark. So we've got 5 more things to do. We've done the first 2. So let's get into it. Okay. So I guess we're going to look at when does U be a vector space of V formally. So the first condition, which we've already got here, is that U has to be a subset of V. If U is not a subset of V, it's never going to be a vector space. That's the first thing to note. Then for U, a subspace of V, all it essentially is we've got V, which we've already talked about, could be expressed, and I think this will be useful here, so I'm going to, in this form. And by the way, for all of this, I could have put this in this section, I decided not to. A vector is just an element of a vector space, so if, which it just so happens it is, the matrices, which we might write like this, the 2 by 2 matrices maybe, with real elements. Elements of this, let's say A, because this forms a vector space with some standard operations over matrices, and over square matrices and also over the reals, it means that A can sometimes be thought of in a vector in this concept. So here, and really the whole of this vector spaces series, a vector is more something that belongs to a vector space than anything else. Okay, so we have vector space, and we're going to use this notation for it. Oh. Yeah, I need to put my keyboard not on a higher place where it can fall easily. Alright, we'll get there. Oh, what's going on? Okay. It's going to be messy, but that's fine. Alright, so we got V given by this, and then we got U. So it's a subset, and for the test, if it's a vector space, we just say it inherits that. Seeing as we're going to have the same type of elements because it's a subset, it's reasonable to use the same operations, and that's just what you do. Oh no, wait, that should be U, not V. Oh, this is very confusing because I tend to do very curly stuff. Gotta make it a sharp V. Okay. Alright. So, U, a subset of V, is also a subspace if this new thing we've got here is itself a vector space. So, pretty simple, really. But we have some nice little tricks that means that we've done this in a previous chapter, if I've got that, but this is a quick little, the axioms list I wrote for when a vector space is a vector space. I didn't bother to expand like property / axiom 1 about abelian groups because I wasn't really thinking about it, but in general you're going to have this be an abelian group just by the things we tend to shove into our vector space definitions for when we're saying let a vector space exist. But then I condensed it into this. So this is, it doesn't look like that much, but it's maybe oftentimes about 20-30 minutes of work in terms of like writing stuff out to prove this. Maybe less if you're quick, but it can be quite tedious to really prove all 6 properties. But this is what you'd need to do if we didn't have a couple theorems and lemmas we're going to look at in a second to prove that something is therefore a vector subspace because it's a vector space and it's also a subset, which I already thought about that way. It's actually really, really simple. Just it's a vector space and it's a subset. This is a simple chapter, but I guess because you're only just getting used to vector space at this point is why it can sometimes be tricky. But it's really not that bad. There it is. So I thought I'd put this as a small aside. This is what you'd have to do if it wasn't for a few tricks we're going to look at. I'll just write a quick sentence here. So U is a subspace of V. Put this in like squiggly brackets to suggest we're just making a note. U is that, V is this, and U is such. It is successfully, maybe? Not the best way of writing ever, but whatever. Successfully subject to the 6 axioms of definition. I'm not going to write definition out to save time. Definition 1.1, which we will have looked at in chapter 1, but this is chapter 3. But I've also included them here. These are the 6, but we'll do that in more detail in chapter 1, I'm sure, in 1 or 2 episodes maybe. Okay, and that's the end of our definition. And so now we move on to a quick notation thing. I mean, I'm being overly verbose for sure with this, but I think it doesn't hurt to be thorough with your maths. Just we're going to say, say U is not. Oh wait, did I? Yeah, I did remember to do the underline. You say U not a subspace of V if U is not a, I'll be extra verbose, vector subspace of V. Okay. That's just a quick notation. What are we on? 3.4. Alright, and we continue. Alright, so what next? Okay, so we're going to look at a very formal theorem that, yeah, we're going to look at like the formal theorem, which is very nice, and with this you can do everything really, but then we're going to refine the techniques we're going to use if you were to do some calculations with some following lemmas and remarks. So, put in brackets, not for calculations. So you're never really ever going to actually use this per se, probably, but it's nice just to write out some things that are true about math stuff, you know? That's what we do in pure maths. Okay, so, okay, suppose V a vector space and U a subset of V. So you might be a subspace, it might not. But then, instead of having to go through all 6 axioms, we can now... Alright, we're just going to set up some formalities first. So we're going to say suppose vector... Oh, and I use a bar above a letter to show a vector rather than underline. It's just how I do it. Suppose u... I'm going to give the u and v a hat like that. Not a hat, I'd take... Suppose u and v of u. And suppose lambda is of the field, which is going to be in the vector space. I'll write this over here. This is the vector space we're working with. Alright, so we've sort of defined what we're doing here. And then we're going to have our result here. Then U is a subspace. It's not very... No, it's fine. Subspace if and only if both of these 2 conditions hold. One, we're going to have U plus V of the set of U. And I'm going to add something over there in a second, but not yet. Just here. And also we're going to have lambda U of the set U. And that's our theorem. So, what's going on here? I mean, first of all, the way we've done suppose is we're saying this is true. I guess I could put it down here. We're saying 1 and 2 are true for all uv of u for all lambda of f. And so we're saying these simple operations, we're just going to add the 2, and if whenever you take u and v of u, the adding of them is in u, and also lambda u is in u, then we're saying that u is itself a vector space, and also a vector subspace of v. So if we go over to here real quick, because I thought this would be fun, this is actually one of the axioms from here, but we're only using some of them. So we got this one, that lambda scalar multiplication of a is of v. And I haven't shown what lambda and a are. This is just a quick sketch of the axioms. What's the other one we've used? Oh, and u plus v isn't even on here. We have a more complex version here of... I guess this is the one that's closest to the u plus v one, but it's more complicated, but we've condensed it right down. So we really cut out a lot of the work here, and we could do a proof. I'll probably maybe do that on a later episode of this chapter, but for now I just want to leave it as this is what you do, and this is not too bad to do. And this is saying is a vector space, because we're also going to look at how, vector subspace, which is a vector space, but it's a vector subspace. Oh boy, I'm not going to put a square around it, that's not going so well. Okay, and essentially this can roughly be thought of closed under addition, and this can be thought of as closed under, but I put it in quotation marks because it's kind of like, as we saw with this one, it's not even really an axiom, but we can use this. But you wouldn't really actually use this to say it's a subspace, as I put not for calculations, because it turns out there's a quick shorthand of this shorthand. We can go even more efficient, and that leads us on nicely to lemma 3.6. I could have done lemma 3.6 or mark 3.7 either way, but I felt it was clearer to do how to show something is a subspace first, then show how to show it isn't. So we're going to do it this way, and it's really, really quick. U subspace of V if and only if U plus lambda V of the set U for all U V. Oh, I forgot the tick on my V. The set U for all lambda of the set of field. And that is it. So we basically just combine the 2 results there, and you can do a quick proof to show that this is equivalent to this. You can kind of already see it, to be fair. I guess, yeah, I mean, to be honest, it's kind of like if you did these in reverse order and then combined is essentially what we're doing here. So by doing the v lambda, we're sort of kind of saying it's part of it. Yeah, you have to do a quick proof to show it, but it turns out these two are equivalent. So you can just do this to show it as a vector subspace. But what about if it isn't? How do we go about that? Well, in reality, all you do is just use Theorem 3.5 in reverse. But just to be extra clear about that, we're going to write it as a remark here. Namely, showing U not a subspace. That's so curly. There we go. Not a subspace of V. Find a counterexample. Of the form 1 U plus V not of the set U, or 2 lambda U not of the set I'm going to write this out in more words than maybe I need to, but just to make it really clear what's going on here. For some U of U, for some V of U, for some lambda of the set field. Okay, and that's all. And this will be clearer with an example, but you can kind of see what's going on. We're just doing Theorem 7.10 reverse, to be honest. Sorry, not 7.10, 3.5. Yeah. The thing is, I don't know why I bothered doing that, because it is just the same thing, but sometimes seeing logical inverses isn't the most immediate thing. So, all we've done is swap the of the set for not of the set, this to or, and then the for any to for some, and you get an exact logical not thing, which isn't necessarily that important, but yeah. And we've come to the conclusion of what we wanted to cover today. So, how long was that in the end? I think I've made it less than half an hour, I think about 24-25 minutes. I'm going to end the video as soon as I can after this, just to make the video not too long. But yeah, essentially this jumpre versus vector spaces slash maths series slash maths for lazy mathematicians series is basically going to be trying to cover as much stuff as I can as quick as possible and sort of do quick hands for as much as I can. Although I definitely could have done more quick hands here, but just I wanted clarity for this episode. Let me know what you think. Might redo this episode, might be more episodes chapter 3, or I might just go straight on to chapter 4. We'll see what happens. But yeah, thanks for watching, and I'll see you guys shortly. Bye!